As thermal motion of atoms increases, temperature also increases. There seems to be no upper limit of temperature, but there is a definite limit at the other end of the temperature scale. If we continually decrease the thermal motion of atoms in a substance, the temperature will drop. Absolute zero is the temperature at which no more energy can be extracted from a substance. At absolute zero, no further lowering of the temperature is possible. This temperature is 273 degrees below zero on the Celsius scale. Absolute zero corresponds to 0 degrees on the Kelvin or thermodynamic scale and is written 0K, short for 0 Kelvin. Unlike the Celsius scale, there are no negative numbers on the thermodynamic scale. However, degrees on the Kelvin scale are the same size as those on the Celsius scale. Ice melts at 0 Celsius or 273 Kelvin, and water boils at 100 degrees Celsius or 373 degrees Kelvin. Here's a chart showing the absolute temperatures of various objects and phenomena. In the 18th century, heat was thought to be an invisible fluid called caloric, which flowed like water from hot objects to cold objects. In the 1840s, James Joule demonstrated that the flow of heat was nothing more than the flow of energy itself, and so the caloric theory of heat was gradually abandoned. Today we view heat as a form of energy that can neither be created nor destroyed. The first law of thermodynamics is the law of conservation of energy applied to thermal systems. By system, we mean any group of atoms, molecules, particles, or objects we wish to deal with. The system may be the steam in a steam engine, the whole Earth's atmosphere, or even the body of a living creature. It's important to define what is contained within the system as well as what's outside of it. If we add heat energy to a system, the added energy does one or both of two things: increases the internal energy of the system if it remains in the system, or does external work if it leaves the system. So the first law of thermodynamics states, heat added equals the increase in internal energy plus the external work done by the system. Let's say you put an air-filled, rigid, airtight can on a hot plate and add a certain amount of energy to the can. The can has a fixed volume and the walls of the can don't move, so no work is done. All of the heat going into the can increases the internal energy of the enclosed air, so its temperature rises. Now suppose we replace the can with a balloon. As the air is heated, it expands, exerting a force for some distance on the surrounding atmosphere. Some of the heat added goes into doing work, so less of the added heat goes into increasing the enclosed air's internal energy. The temperature of the enclosed air will be lower than that of the air in the closed can. When a given quantity of heat is supplied to a steam engine, some of this heat increases the internal energy of the steam. The rest is transformed into mechanical work as the steam pushes a piston outward. Adding heat isn't the only way to increase the internal energy of a system. If we set the heat added part of the first law to zero, changes in internal energy are equal to the work done on or by the system. If work is done on a system, compressing it for example, the internal energy will increase and the temperature of the system rises without any heat input. If work is done by the system, expanding against its surroundings for example, the system's internal energy will decrease. With no heat extracted, the system cools. When we pump on a bicycle pump, it becomes hot because we put mechanical work into the system and raise its internal energy.